My name is Max Wetherington, talking about molecular spectroscopy across length scales. To begin, molecular spectroscopy simply is the study of light interaction with matter. This basically summarizes everything here. So some spectrum of the light that we use, and we can look at different ways in which the light interacts with that sample, if it reflects, transmits, absorbs, or scatters. And then we need some detector to measure that change in light. This is a nice graphic from Evans Analytical Lab where they kind of show a bunch of different techniques, their sensitivity for different components across different length scales. And I've highlighted a couple of these here, which we'll discuss today, in addition to Micro-UV-Vis, which is not listed on this graphic, which kind of falls in the same area as like Raman to FTIR range. So you can see the length scales here down on the bottom. We kind of cross over this threshold. So everything's like micron and above. And then there's some other new techniques that we have that are sub-micron. And specifically, we'll talk about Nano-IR, or it's also called AFM-IR. What dictates our length scale that we can study really depends on a couple of variables, but mostly there's either the different detection method that we use. Most often we're using lenses to focus the light, but then there are some other novel techniques which we'll discuss, which we kind of just categorize as near-field spectroscopy, where we kind of break below the limit of what we can reach with just a lens, focusing light through a lens. And then, of course, the wavelength of the light that we're using will also dictate the length scale at which we can characterize your material. So I'm going to go through and give a couple of examples, kind of working from the macro to the nano, starting off with Micro-UV-Vis. This is a project done here with Tuxing Wong's group, where they looked at these leafhopper insects. They have these cool, what they call brochosomal spheres that actually demonstrate really amazing anti-reflection properties. And that's what this whole project was effectively studying their efficacy across the spectral range of interest. So using a Micro-UV-Vis, our spot size in this case is on the scale of like 1 to 10 millimeters, looking at different surfaces that they treated, starting with like a substrate, then putting silver down, and then looking at the effect of metal-treated unique brochosomal spheres. And so again, this is a large length scale kind of measurement that we can do on our systems. We can look at it in reflectance. We can do transmittance and diffuse and or specular measurements as well. This is an example of a mid-IR measurement. This was a project where they were looking at some paintings. They wanted to detect the type of pigments that were used for archaeological and historical importance. There's a couple of ways we can do this in the mid-IR. One is you can actually use what's called an attenuated total reflectance measurement, where you actually push a crystal down onto a surface. That's not ideal for a painting that you want to preserve. So another method of doing this is you can just measure the reflectance of the IR off the surface. And so doing that, they're able to distinguish, different pigments across this whole painting while preserving the painting, which is very important, obviously. So that is a technique we have here. It's something we actually worked with other researchers across Penn State as well. And then my last macro example is we have a recently acquired tool in our suite of Raman spectroscopy capabilities. Raman is a form of scattering. So this is a scattered light interaction where it's actually inelastic scattering. So light changes energy after interacting with the sample. And that change in energy corresponds to vibrational state changes in your material. I kind of assume you have some background in molecular spectroscopy because I don't have time to kind of go through all of that. But in this case, this is a macro Raman measurement where we actually use a probe and we can insert that, in this case, maybe in a emulsion. And this is what was done here is actually, this is a two-step polymerization where they have the monomer seed at different stages, and they can monitor the reaction of the monomer to polymer. basically by the disappearance of the monomer response, the spectral response of the monomer. They validated this in situ monitoring by taking samples out at different time intervals and testing it with gas chromatography. And so you can see that there's pretty good agreement between the Raman measurements that's in situ, which gives you much better temporal resolution, and you don't have to remove the material, compared to the GC. And what's important about this for this particular process was that, this is a in this polymerization, that the goal was to have like a particular shape, and it was really, they had to have tight conditions on their growth process to achieve that particular polymer shape. And so this way they kind of have a real-time feedback of the rate of consumption and reaction. So stepping down now into the micro scale. So now we're submicron, focusing this light through a lens. In this case, this is Raman spectroscopy again. This sample is, or this project is one of the IRG projects funded at Penn State, which is referred to as 2D polar metals, where these metals are actually intercalated between this layer of graphene and silicon carbide. Turns out these metals actually have very unique spectral response, which we can measure in the low frequency in Raman, which is also a specialized capability we have here at Penn State in MCL. And we can then take that signature in the low frequency and map out the distribution of these 2D metals. So we actually have two different phases for a given metal. So this is silver, and we still are trying to understand this, actually, what that actually really means. But we know that there are at least unique spectral responses for these two systems compared to just areas where there's no metal intercalation. So we can compare this to optical microscopy as well. So there's also, each of these has just the ability to image your sample in addition to acquiring the Raman spectra on the same length scale. Recently, we've now added the ability to do Micro-UV-Vis spectrophotometry on the same tool, so on the same Raman instrument. So now we can measure in this case was reflection, but we can also do transmission measurements. We can map out the absorption profile of these two different phases. And then you can actually go through and pick points within this map and then just take the Raman spectra within this region. An advantage of that is the Raman maps that I just showed on the last slide, I didn't really highlight. They take hours to acquire. This is only 10 by 10 micron area with, roughly submicron resolution. Here, this is approximately a slightly larger area, and we can do it in 1 minute. So this is a much better way to screen your sample and kind of highlight different regions that you might want to investigate further with Raman spectroscopy in this particular case. So we also have the ability to do micro FTIR. In this case, this is a transmission measurement. These are the seeds of maize roots. And this project was studying the effect of the anatomy of the seed and its efficacy in growing in compacted soil. Turns out that when there's this is a lignin-rich, I'm not going to even try to pronounce this word. If you have questions about that, talk to me after. But either way, it corresponds basically to a lignin-rich outer layer, which turns out to help these particular genotypes grow in. They're a little bit more drought resistant, and they can grow in compacted soil a little bit more, better. And with the FTIR, our resolution is a little bit larger. So it's on the 10 micron to 200 micron length scale compared to the Raman. And that's because the wavelength of light that we're using is in the infrared. So it's a longer wavelength. So our spatial resolution is not quite as good as what we can achieve in the visible. But I'll show you in a little bit ways to get around that. And that's what I'm going to show here. So we have the kind of far field approach, which is where we focus light through a lens. And in that case, we're limited, again, by the wavelength of light, and what's called the numerical aperture of your lens will dictate the spot size. This is an airy disk. And basically our ability to resolve this is what defines this spatial resolution. The near field approaches all use something slightly different, but most of them, all of these that I'm showing here, use a scanning probe microscope to somehow overcome this limit here in the far field. We actually have all three of these tools. So tip-enhanced Raman we have in MCL. The scattering SNAM is available in another user facility in the basement, and Nano-IR is in MCL. Tip-enhanced Raman is limiting because there are only a very small subset of materials that actually work for tip-enhanced Raman. So that makes this a challenging tool to work across a whole range of applications. Scattering SNAM is extremely time-consuming and is very difficult to work with, but you can work across a wide range of materials. So that's not a limiting factor in this case, but it is more just the time consumption. Nano-IR is the most turnkey near-field spectroscopy technique that is out there right now. We can likely get you data within a day, typically, and there is less material selectivity for this particular technique. So kind of how it works, quick overview here. We shine the IR light onto the sample, and that light will be absorbed by the material if there is a given, vibrational state change that corresponds with the energy of light. So it's still infrared spectroscopy. But in this case, the way that the detection works is really novel. This was what kind of was pretty special and what differentiates it from the other near-field techniques where all of these, tip-enhanced Raman and scattering SNAM, we're measuring, so it's light in and you're measuring the light coming out. With Nano-IR, you're shining light in and your cantilever is your detector. And so this is what's really novel about this particular technique, because it's extremely difficult to differentiate the light that's scattered from a femtoliter of volume up from your sample compared to the giant spot that you're irradiating your sample with, the far field light. And you have to use tricks to basically overcome that. Where in this case, you're using the incredible sensitivity of this probe to act as your detector. And so that's what's happened. The light is absorbed, it heats up the sample. That sample will expand. That expansion is then measured by the cantilever. And so that's then how we convert this, this irradiation to this measured spectral response. And so we actually have tunable lasers that we sweep over the spectral range of interest. We pulse it, heat up the sample, it expands, we measure that expansion, and we can get this spectral profile from your sample. And the resolution is really good. So here, this is a copolymer blend of PMMA and polystyrene, and the resolution is on the order of 10 nanometers. The one thing, so that's the lateral resolution is great. The axial resolution can be not so great. There are different modes that we can use for this particular Nano-IR technique. One is contact AFM-IR mode or volume probe, where you're really measuring an integrated area below the surface of your sample. So there's really no axial resolution. It's just the entire sample is basically expanding. You're measuring the expansion of that whole material. So axially, we don't have great resolution in this particular mode, but we also have this other nonlinear force detection or heterodyne force detection mode where we're mixing two waves, and that gives us much greater surface sensitivity. And so in this experiment here, this is PMMA that was drop cast on a substrate. And so it's just kind of like this wedge here. So they're looking at the height profile, this just kind of this slope. And when we use the contact or volume probe method, we see that the intensity of the IR response just scales linearly with the thickness of the material. When we use the surface probe measurement, we see that it kind of reaches some plateau after about like 20 to 30 nanometers, and that IR signal intensity is constant. So it's showing us that we're actually, that the axial resolution is on the order of, let's say, less than 50 nanometers, because it is material specific. So in this case, this is looking at a STEM section. The interest here was the goal was to see if we could map out the structure and orientation of cellulose at these different walls within the stem section, and also just kind of as an acid test, can we show the distribution or higher concentration of pectin within this middle within the middle lamella. And with this contact IR mode, our lateral resolution looks nice, but we can't. So here we're mapping out the pectin response with respect to the cellulose, and there should be a nice kind of line right here in the center. We don't really see that. It's a pretty blurred out response. And that's because we're using this contact IR mode. So we're really averaging axially all the way through this stem section, and we may not be perfectly on axis with this middle lamella. So this, although gives us kind of an interesting image, was not really able to achieve this. So it highlights the fact that although lateral resolution is great, if you're trying to look at a heterogeneous material system, and how you prep that sample can matter a lot, depending on which particular mode you're using for this measurement. This was another project where we looked at nano-indented glass. As the glass is indented, we see densification of the silicate. And we see that here in the IR response where we see this shift to lower wave number. And then after that indentation, the glass was annealed. You see there's still an indent here, so there still should be some densification, yet we can't really resolve that, again, with this contact IR mode. So this kind of highlights some of the limitations axially. So here, this is 80 nanometers. We actually do see a shift. Once it's annealed, we're only about like a 30 nanometer indent. We no longer can see that. At the time, we had not really, we didn't have the surface sensitive mode. This is actually something we've recently added. And it, as you can imagine, when we're now working with two waves rather than one wave, things can get a little bit more complicated. So we have started to use that particular mode. I just didn't have any projects that I was allowed to show that could highlight that particular technique yet. But in this case, feasibly, we would still see this shift in the SIO stretch from the silicate. And then just the last kind of idea to pitch here is that we have worked on several projects where we just use this particular technique to help identify contaminants on the surface. And IR, generally speaking, has greater sensitivity to organics, but we can also detect inorganics as shown here on various substrates. So with that, take any questions, and thanks for your interest.
Thanks so much. This is fascinating stuff. I'm coming from a natural science side of things, and I guess I'm interested with these newer techniques. It's awesome that they're smaller. Have libraries of standards, like for minerals or for natural compounds, been made of these, or sort of for applying to in situ samples? What's the state of that?
So
where you sort of don't know what's in them.
Okay. Well, so infrared spectroscopy and Raman spectroscopy has been around for a while, and there are databases available for those techniques. The nice thing about this Nano-IR is that in most cases, I'm not sure this is exactly the question you're asking, but the IR response is very comparable to in the Nano-IR as it is in the FAR-IR. There are some caveats to that. I can get into that, but that's kind of a little bit more in the weeds. So just simply speaking, there you can compare the spectral response that we're seeing with Nano-IR to the measurements we see with FAR-IR, near far field IR. And there are databases out there for all sorts of minerals, pigments, polymers. I mean, that there's a wealth of data that exists out there. We also have access to one of those libraries. It is not completely comprehensive, and it's quite honestly a challenge to have something that is comprehensive. This is a plus and a minus of molecular spectroscopy is that, since it is vibrational spectroscopy, the spectral response is not only unique to the composition, but also the structure, the environment, its orientation. So that specificity can be very useful. It can also be very challenging when you're trying to interpret the data. So there could be millions of different spectra for all the millions of different materials. So it's difficult to have access to the whole library of materials. I hope that answered your question. Okay.
So if I had say particles that are a couple hundred nanometers, what would be a way to sort of prepare these to do Nano-IR? And I'm interested in just what are they, like, not contamination, but it's atmospheric chemistry, some other nanoscale additive, and average particles 400 nanometers just to make it up. Like, what would a prep look like for that?
So we can prep in a number of ways. If they're large enough, so I still feel that far field is a good place to start. Anytime. Even if we think that we need to go to Nano-IR, it's because it is a bit more time consuming. We can still check your materials with Raman or micro FTIR. Could be a faster approach. But as far as prep for Nano-IR, there's different substrates we can use. If you have just suspensions, we can drop cast onto gold, or IR transparent windows work as well. You can, if you have, powders, just free powders. I mean, there's a number of ways for us to prep those materials. Some things might be a little bit more complicated. We have started looking at how we can look at multiple films. So looking at like microtoming or fibbing the cross section. We've done some microtoming. We're planning to explore some fib cross sections and see how we can look at the interface between layers, because that's certainly of interest for a lot of individuals. But any other questions?
Sorry, sticking with the preparation, if you were working, I guess I know so little about this. So for sample prep, you talked about powders. If you were working, say, with fine minerals, could you just crush those puppies and then they could be prepared for Nano-IR or tip-enhanced Raman?
Yeah. Again, the fact that we can look across length scales is great. I encourage individuals to always start larger scale. So if we have minerals, let's say, let me just put this in perspective. So, these measurements, they will take one day, versus, we could probably do these measurements on if you have a bulk sample, we could do those measurements on Raman in 10 minutes. So it's always good to start even with just optical microscopy, kind of work your way through to help us identify what is the question we're trying to answer at this length scale, because we can't look over a large area with this particular technique. This is all about looking at the highest resolution we can achieve. So if there is an interface, or if you're looking for a contaminant that's really small, or if you're trying to map out heterogeneity on the nanometer length scale, those are things that I think Nano-IR is suited to help answer. But before you jump to that, I think there are maybe things we can do with just our standard kind of spectroscopy techniques that can certainly help, identify the composition or, contaminants or strain, orientation. As I mentioned, all of these things can show up in the molecular spectral response. Any other questions, thoughts? By the way, if you want to find any more information about this, you can look on the mri.psu/materials characterization lab webpage. We have all the tools listed, the capabilities. We have pretty much every accessory you can think of for all these tools. All right. Thank you very much. Bye.